Hello, hello, everybody, and welcome to the Smoko podcast. My name is Alexis Armstrong, your host. Nice to meet you. The Smoko podcast is the place to celebrate and highlight women working within STEM and trade occupations. Tune in, take a break. We're on Smoko. And today we're extremely lucky to be joined by the lovely Dr. Suzanne O'Connell. Dr. O'Connell is a professor of earth and environmental science at Wesleyan University in Connecticut. She has an extensive career both as a professor and a researcher where her research is specific to climate change and climate science. She studies how polar regions, specifically the North Atlantic and Antarctica, how those have changed in the past, and using that understanding to try to better understand what's going to happen in the future and model the future of climate change. So her research is heavily tied to one of her passions in life, which is scientific ocean drilling. She's been involved in SOD or scientific ocean drilling since 1978, and she's done numerous scientific expeditions. I think her tally is at 9, but it might be a little bit higher than that now or soon to be higher than 9. So we're going to talk all things SOD. We're also going to talk about another passion in her professional and personal life, which is DEI. In 2015, she co-edited and authored the book Women in the Geoscience, Practical Positive Practices Towards Parity, and several journal articles, which include like Leaks in the Pipeline, Why Do Women Remain Curiously Absent from the Ranks of Academic, in addition to being involved with numerous community organizations and associations, like the Association for Women Geoscientists, started the On to the Future at the Geological Society of America, and then 1 year at MIT on a National Science Foundation visiting professorship for women. So she's done loads of work with DEI. So I'm so excited to have this conversation with her today and talk to Dr. O'Connell about all things her research, scientific ocean drilling, and then DEI. So, Suzanne, thank you so much for coming onto the show. I appreciate it immensely.
It is such an honor to be here. There are so many things I like to talk about, and you've just mentioned a very large part of them. So thank you for inviting me.
You're welcome. It's amazing to have you on. It's so nice to see you again. We met a while ago when we were both down in Antarctica on IODP, and it's just so nice to see you again and to have you onto the show. So thank you for coming. And maybe to start us off, because you're interested in so many things and you've done so many things, maybe to start us off is how did you get first discovered and first interested in oceanography and climate science? Because you have a BA in biology and geology, MSc and a PhD in geology, and then an extensive career as a professor of earth and environmental science and researcher at Wesleyan University. How did all these things come to be?
And this is a question that I deal a lot with students because I teach primarily undergraduates, and they're all nervous about what they're going to do when they grow up. And I tell them, I don't know what I'm going to do when I grow up, but I'm running out of time. So I got to figure it out. So I think there are some people who know what they want to do, like maybe the moment they're born, or certainly by the time they're 5, and they just follow that path straight. And I have a very unstraight path. I got interested in lots of things. And so sometimes say it's like when I was a kid, we used to think about Dalmatians. Whenever they saw a fire truck, they'd just have to run behind the fire truck. That's sort of how I feel. So I grew up in a really rural part of Massachusetts. It was a very rural area. There was a one-room schoolhouse in our town. We had to travel 18 miles to high school. And it was,
Rural.
I also come from a big family. I have 5 younger sisters. One of the great ways to get away and have a little space for yourself is outside. So I had this little secret place outside because it was rural and in the woods, and I had a little place to sit, and I could leave things there to read and just vegetate. And I loved it there, and it was quiet and no one was asking you to do stuff. So then when I went to college, it made sense to major in biology because there were a lot of plants, and
Yeah, you're used to it.
and biology goes with plants. And then one summer, I was very fortunate to be a teaching assistant at a small college in Maine that was a third biology, really botany, a third zoology, and a third geology. I had never even considered geology because, I don't know, miners and oil people, and it just didn't seem right to me. But I took this course. So this was the summer of probably 72,
Okay.
maybe 71. This was just when plate tectonics was coming into
Wow.
this geologist was telling me that we were in the White Mountains of New Hampshire and that some people believe they were linked up to the New England seamounts in the ocean. It's like, give me a break.
You're like, "They can't be linked. There's no way."
How is this possible? So then when I went back to college, I said, I better take a geology course and get straightened out since I've been hearing all this really
Nonsense.
like rubbish nonsense over the summer. So I took a course in geology and it was just life changing. The culture was so
Mm,
different. In biology, the professors were all doctor this and doctor that, and very formal, excellent, but formal. And we were in geology, they were first name bases. We had a big rock garden with rocks, and we'd have lunch out there together and talk about rocks. I thought, this is so fascinating. I said, plate tectonics was coming on board, and they, for some reason, were managed to get some of the most exciting people on the edge of plate tectonics to come and speak to us.
oh, amazing.
It was unbelievable. And the fact that plates were moving around and ocean crust was forming and we didn't quite know how it formed. And one of the people who came to talk was someone who studied ophiolites in Newfoundland. And
Cool.
ophiolites are when oceans, sometimes when they collide, a collision happens, bits of ocean crust get smushed up onto the land. So you can walk on the mantle, you can walk on the crust, you can see the different layers of ocean. So you
And to
just
see it.
walk on this simple structure in Newfoundland. I was like, man, if I ever go to grad school, that's what I want to do.
Mhm.
But then I didn't want to go to grad school. I was sick of school. So I got this great job teaching in Yosemite National Park. And to be there all year, so you get to see the seasons.
Mm.
And we had students from all over California come up and spend the week, and we would teach them cross country skiing, and then we would hike them up Yosemite Falls and teach them about the natives that lived there and all the plants. It was just terrific. But while I was there, I got really interested in photography. So this was another slight diversion.
Yeah, I didn't know that. I didn't know that you were a photographer. That's
Yeah.
cool.
I actually learned to print in Ansel Adams' darkroom.
Oh, what? That's a big flag, Suzanne. That's crazy.
It is crazy. And I decided I just love photography. So I decided I really wanted to be a photographer.
Mm.
But I had a lot of student loans and we get paid like $10 a day in Yosemite. So I couldn't afford to be there. I moved back to my home in Massachusetts and tried to like work as a photographer. But I am so far from a business person. And I realized I hated it. And I said, well, I guess what I'll do is I'll go to graduate school and get a master's and work for an oil company. And I can support this photography habit.
Oh, okay. That's how you started.
Well, I started. So I said, I'm going to go support this photography habit. And so, of course, I was going to map ophiolites in Newfoundland
Mm.
because
They're
that was
so cool. Why
cool.
not?
Even though it has nothing to do with oil or anything like that. If I really was thinking straight, I would have gone to like UT Austin or something. So I was mapping ophiolites in Newfoundland. And then at those days, the organization that did the planning for the drilling ship, which in those days was called the Glomar Challenger, there were different panels that would decide what to do. And one day I was in my field area on the top of Table Mountain in Vaughan Bay, Newfoundland, and who comes wandering by but the ocean crust panel. So all these guys are coming in, they're all interested in how you make ocean crust. I was interested in how you make
Yeah.
crust. So I showed them around a few places. And then there are also ophiolites in northern Newfoundland, and they were heading up there. So I didn't have a car. So I said, oh, can I go with you? And they said, sure. So I went with them and I got talking to them. And it turns out that one of the people on this trip was someone who was going to become the new head of Joint Oceanographic Institutions for Deep Earth Sampling.
Oh my goodness.
So he said, oh, you should, if you're really interested, you could apply. And I said, that sounds great, because I was getting tired of school again.
Yes.
In those days, I mean, I had heard about the Glomar Challenger. And the reason it seemed so special was when I was an undergraduate, there was a woman, of course, like all my professors were men,
Yeah.
and most of the students were men. And, but these male professors talked in these sort of hushed tones about this woman, Helen Foreman, who had been on the Glomar Challenger.
Yeah, it was like that thing of legend.
Gosh, she didn't have an office down with where we were, but she had an office somewhere high up in the rafters or something.
Yeah.
I saw her float by every once in a while. And I was like, oh my gosh.
There she is.
When I knew that I could start working and being involved with this amazing ship, the Glomar Challenger, I said, oh, okay. So I applied, got the job, and I spent 2 years as the science coordinator for
What's all?
Joint Oceanographic Institutions for Deep Earth Sampling, JOIDES.
Very
And
cool.
so it was a fantastic job because I hadn't traveled much. I've been to Canada, but this is an international program. So I went to the Soviet Union twice.
Whoa. That's cool
Mhm.
back in the day.
Back
That's
in the day,
insane.
and Iceland and Italy. And it was with these really interesting people. But I realized that I was very much a second-class citizen because I only had a master's degree, and I was around people who all had PhDs and people at Woods Hole all who had PhDs. In fact, early on, one of my first encounters with one of the members of the planning committee introduced me and said, "Oh, this is Jim's gal Friday." It's like, "Excuse me?
Oh, yeah, no, absolutely not.
You have a master's degree," and I did publish a paper, but it was just if you didn't have a PhD, you didn't count.
Yep.
So I decided, okay, I really like these guys and I like playing this game. I said, I better get myself a PhD. So I applied to a couple of schools and I got into a couple of schools, and one was Columbia. And I was trying to decide whether to go to Columbia or Scripps. But I had been in Woods Hole, and as a single female in a town where most people are married and they have
Mhm.
children and they have gardens, and I was traveling. I didn't have a garden and I wasn't married and I wasn't interested in children. So going to Scripps just seemed like going into another woods hole. It's
Yes. Yeah.
beautiful. It's on the ocean, but it's very insular versus New York. And I was trying to make the decision. When I went to New York, there was a subway strike. And so maybe even a taxi strike. I don't know. It was some big strike. And everybody was just walking around carrying their dress up shoes. And I thought, "This is so cool."
This has energy to it.
Yeah,
Yeah.
vibrant. To be in a real big city just seemed perfect. So I went to Columbia, and where we always joke that Columbia keeps its geologists up the river. They don't let us downtown on the main campus. So as I was going out, because I finished my job in July, the 2-year rotation, and the science coordinator job was also moving to Scripps, and I could have gone to Scripps and keep my same job, but I didn't wanna do that. So I didn't do that. And
Mhm.
the person planning who got to go on the ship, and it was amazing that it was very much smaller for those people who've been on the JOIDES resolution, which has been around now for over 40 years.
Ages.
The Challenger, there were maybe 12 scientists and maybe 12 technicians, so it
So
was so
tiny.
much smaller. It was a smaller ship, not as able to drill in waters that are ice infested or
Mhm.
rough seas and stuff like that, which is partly why they tied it up and got a new ship. But the person doing the deciding where people would stay, who could go on the ship, said, "Would you like to go out?"
That simple. You're like, "Yeah, duh."
Oh my god. Yes, I never would have asked, it was
Yeah.
such a dream. I couldn't imagine asking. So I said, "Yes." And so we went, and it was Lake 74. It was Cape Town to Swakopmund, which was then Southwest Africa, now Namibia. It was a really fun expedition. But the real story, I was looking at some of the basalt because we were drilling on a place called the Walvis Ridge in the
Mm.
South Atlantic. Still being an ophiolite person, I was looking at the basalts and stuff, and there really wasn't too much you could do with the basalts. Real story was in the sediments.
Yeah.
And so gradually moved towards sediments. And so I did a lot of work with side scan sonar, looking at the ocean floor. We know so little about the ocean
Yeah.
floor.
Still to this day.
No.
Yeah.
It's crazy. It's, what you think we've walked on the moon, but we haven't walked on the ocean floor, which is crazy. So anyway, so then I stayed at Lamont and I worked on deep sea sediment, primarily their surface features with side scan sonar, and then cores, some piston cores. And then I got to go out on Lake 96, the last expedition of the
Oh, the
Challenger, which
Glomar.
was really a very sad expedition because the same people had been working since the very beginning. It was very sad, but it was a great leg. Oh my gosh. Looking at all this sand in those days, people didn't believe that sand would travel all to the deep ocean floor, but there's so much
Really?
sand in the deep ocean floor.
Because turbinates were barely understood at that time and it was
Yeah.
just starting.
We knew there was that in 1929, there was a break in the cables in the North Atlantic, which is their first, not discovery, but interpretation of turbidites. But I remember even on Leg 113, people telling me, because we were drilling, if you remember, 694 right in the middle of the Weddell Sea. People saying, there's not going to be any sand there. And I'm saying, that's where all the sand is going to be. That's where all the sand was, in
Yeah,
the
you're
middle of
right.
the Weddell Sea. Well, because turbidites travel. So it was the same thing in the Mississippi Fan. And with the new side scan and then multi-beam, we didn't have multi-beam then. We would have a single line going across like a channel or something.
Yeah.
So if you look at early maps, like the Hayes and Tharp maps, it shows rivers coming down like this in a deep sea fan. But in fact, they're all anastomosing. It's just like rivers
Oh,
on land.
yes.
Know that. And it makes no sense because it's mud. It's soft mud. How do you,
Mhm.
a channel that can
That
be 100 meters deep in soft mud? But somehow that's what you find. We still don't know that answer to that question. So that was part of what I was working on for my PhD. And then the origin of a lot of this sand and it's where it came from. So then I'd forgotten about working for an oil company now because I was really enjoying what I was doing. I also applied for my deep love, the start of the new ocean drilling program then, the
Mhm.
Joides resolution. And I got that job
That's a staff scientist. That's when you worked
as a
for
staff
yeah.
scientist. Yeah.
I love that story so much, Suzanne, because I love that it's not at the very beginning, we said I'm still waiting to grow up and it's not a straight path and it's trying to figure out where you're gonna go. But I do love how a lot of siblings pushed you towards finding like a outside sanctuary and that fell in like a love of like natural science by just being like, I need to get away from all 5 of you being so loud and ridiculous and I need to go outside. I love how that was like the beginning of it. And then the photography break to be like, okay, fine, I'll go back to grad school just to hit my habit of photography and be able to afford it. I still can't believe that's how you were treated with just a master's, and unfortunately, I feel like that might still persist a little bit in academia and within this culture, but I'm really happy that you decided to go back to do a PhD and be like, "Well, screw you." One thing that came up that you were talking about is, like, the different areas of expertise of going from ophiolites and trying to understand ocean spreading. Couldn't imagine what it'd be like back in the day when you're just discovering plate tectonics and that's on the scene, and then trying to figure it out to see what is this first discovery of that. I think that would be so crazy to be part of. And then now your research is really focused on polar climates and paleoclimate of both the North Atlantic and the Antarctic. Could you maybe walk through why these regions are so important in terms of climate and what's special about these marine sediments? What's different about these systems that they're so important to scientists to try to understand climate?
They are very important. And so made the switch from turbidites to paleooceanography and paleoclimate on Lake 113 because,
Mm.
again, it was all about the sediments. And what happens if we look at a globe today or imagine a map of the globe, we have these major ice sheets in the North Pole and the South Pole. And that's pretty unique in Earth's history.
Yeah.
So if we were to go back 35 million years ago, there would be no ice on either pole. And then around 33 million years ago, the ice started to form on the Antarctic. And particularly a place called the East Antarctica. East Antarctica, I think always confusing because if you're in the South Pole, everything is north.
Yeah, it's true. Yeah.
Well, here we're talking about an east and a west.
You're like, what are you talking about? Yeah.
Which way up? Now it's north.
Yeah.
We think it started to form in these high mountain areas in East Antarctica. How it got to how it started to form, there's still a lot of discussion, but mostly we think what happened was that the continent of Antarctica was separating from Africa and from South America, had water that could flow completely around Antarctica. It's called the Circumantarctic Current, and it ended up thermally isolating Antarctica.
Unique, I feel.
So unique, and it's still thermally isolated. And some people would argue, well, there were other things going on. There was a decrease in carbon, CO2 in the atmosphere. There was a general cooling. So there are other things, but certainly that really enhanced it. So again, the ocean is leading this major climate change where we start making this ice. And then in the northern hemisphere, again, people aren't sure when exactly it started, the northern hemisphere ice started. Some people would put it at around 5 or 6 million years. Some people would put it even closer to 3 million years.
Fairly modern. Yeah.
Yeah, very modern. We're living in a unique time. And what happens, though, is we have these two huge ice masses, like giant refrigerators, on both ends of the Atlantic Ocean. And this is where the Atlantic really comes into play. And so what happens is you get cooling because it's high latitude. The water that's at the surface of the ocean gets really chilled, like down to zero. And then you get ice forming. And when the ice forms, the ice is fresh water. So you have cold and you have fresh water. But if you have fresh water, it means you've expelled salt.
Yes. Yeah.
So now you have salt, haline, thermo, cold.
Yeah.
So thermo-haline circulation. And it starts at these two poles and the water gets colder, saltier, denser, and it sinks. And the amazing thing is that these distinct water masses, whether it's the North Atlantic, it's called North Atlantic deep water, or Antarctic bottom water, they sink to the bottom and they flow under the ocean, right along the ocean floor. And as they're flowing, they're collecting little bits of organic matter that are on the seafloor that are falling down. They're dissolving it. So they're losing some of their oxygen because they're decomposing organic matter. Nutrient rich. And so then what happens is when they get to higher latitudes, and this is particularly important in Antarctica, because you have this water that's been traveling from the North Atlantic all the way to Antarctica, and there are air currents that are blowing the water away from the surface, and so you can't have a hole in the ocean. So the water comes up. It's called upwelling.
Yeah.
Brilliant term. It comes up, upwelling. So it upwells, and then it's bringing nutrients. And when sunlight comes out, it's
Primary
Thanksgiving.
productivity. Yes.
It's Thanksgiving. All the creatures are there. And as you know, when you're in the Southern Ocean around Antarctica, it's full of sea life.
Yes, it is. It is like the best sea life that I've ever seen in my life. I will die with those memories of those humpback whales surrounding our boat. Like, it was one of the coolest things I've ever seen in my life.
And there's so much of it. And then there are all those little penguins, and then they're riding by an iceberg.
Leopards, seals, the whole bit.
Yeah. And whereas most of the oceans, if you were to look at say a chlorophyll, which is the fact that you have photosynthesis going on, map of the ocean, these whole big centers, and really nothing is happening.
They're dead zones. They're nutrient deserts for the most part in like the pelagic zone. Yeah, they're just open, empty.
And so if you're sailing around there, you might see, if you dump some garbage over the side, as people used to do, you might get a shark or something coming by to get a snack, but you aren't going to see sea life. Whereas in the Southern Ocean, you wouldn't get tired. The first whale on the port side. The whole boat sort of lists.
Yes, everyone runs.
Everybody runs. But after 60 days of whale on the port side, it's Can I just look out my window and see?
You get kind of used to it and a little bit, what is it? Spoiled. You just get
Mhm.
spoiled by the how much sea life is down there. So is that what kind of makes it so important and so interesting is just the amount of biodiversity and the amount of nutrients?
And what happens is that because it's so dense and it's flowing, it's actually driving the whole ocean circulation. So it's as if you're pushing, you can think of it as pushing, but it's not quite pushing, but decreasing. Water is decreasing at both poles and flowing along the bottom. And so it's driving ocean circulation. And the thing about Antarctica is it's the one place in the ocean where all of the oceans are connected. You can think of Antarctica. So here's the Atlantic part, here's the Indian Ocean part, and here's the Pacific part. All that water meets at Antarctica. And the densest, coldest water is there and it's moving all that circulation. But it's the fact that you have this cold, dense water that's creating what our climate is like today. And that's one of the things people worry about when we think about climate change is that as we melt the ice sheets, not only do we worry about sea level rise, but we create what's called a freshwater lid. So we have a lot of fresh water and it's not salty.
It's sitting right on top of all
It's
this
going to
deep
sit on
water
top.
circulation.
And so then you're going to shut down major ocean currents like the Gulf Stream. That'll be
Because
quite something. But one of the things that happens in these areas, and which is one of the things I study, is the ocean sediment is made up primarily of bits of terrigenous material. Some gets blown in by the wind, some gets blown in with turbidites, and some gets in the high latitudes dropped by icebergs. So you have those three sources of terrigenous material, and then you have plankton that live there. And the plankton, a lot of them, diatoms and calcareous nanofossils, are photosynthesizers. Some really like it cold, some like it not so cold. And so their shells, or they're called tests, they aren't really shells, are preserved in the sediment. So I don't study these little shells, but the great thing about being on the drilling vessel is
other
there
people
are
do.
there
Yeah, who could tell you what they mean?
they can tell you like, oh my gosh, look, this means it was a particularly ice-infested cold time. I only know one diatom well by name. It's called Eucampia antarctica, and I
Okay.
pick it out. And I think, oh, there's Eucampia antarctica. Like I know anything about diatoms other than they're beautiful. But with my work, I can say, oh my gosh, and now we have lots of these little bits of larger sand and even rocks that fit into the drill bit. And they can only come from icebergs.
Where did this drop stone appear from? Exactly. Where did it drop from? How did melting happen? Where did the ice sheet come from?
Where did it come from? And the fact that if you see them, you know there was ice. So it's that very simple observation.
It's so cool how much information is within marine sediments. And also just being the first person to see that. I feel like
Mhm.
that would be fantastic for your research of being like, it's a puzzle piece of trying to understand past climate and understand how it works. Thank you so much for explaining too, I think, because I think when people aren't in geology, they don't understand or wouldn't even think of that ocean circulation, specifically that polar circulation in Antarctica, is the main driver of climate change. And that is the main controller of ocean circulation. I don't think that instantly comes to people's mind.
No, they don't. And it's because when you think of like this ocean, the surface of the ocean, it's wind driven. The upper part of the ocean is, depending on how you count, no more than 1 kilometer, no more
Yeah.
than 100 meters, and probably much less. And then there's another 2, 3, 4
Yeah.
kilometers of water. And we know so little about it. That's the other crazy thing.
Yeah, know so little about it, but it's such an interesting point in Earth history and Earth past history that we have both of those poles right now existing on our Earth while we're studying them, right? So that not only do we not really understand a lot about currents and about ocean circulation, but just to be in a unique time of Earth history
Mhm.
now to study it is just absolutely fantastic and fascinating.
It is. It is. And to be part of it, it's just thrilling.
We've talked a little bit throughout so far our talking about the SOD. So scientific ocean drilling, and you've
Mhm.
mentioned these expeditions and what the material looks like, what you're getting from it, how you're going to understand climate from this material. Could you maybe speak to a little bit more about the role of cruises in climate science, their importance, and why you're so passionate about them? But you've been a huge component of scientific drilling for so long. Could you speak to that, their importance within climate science?
When we think of, we need a record. So when we think about ocean sediments, they're basically a library. And in that library, instead of the books being lined up like this, they're lined up like this. And so when you take your core and you go down into these sediments, you're bringing up this library of Earth's history. And you could, why don't you do it on land? You can't do it on land because
It's not
the land
preserved.
gets really messed up. It's right,
Yes.
it's not preserved. So we have wind blowing things around. We have, in a lot of places, ice moving, like
Mhm.
pushing stuff away. Like here in Connecticut, we have some glacial lakes, so we have some material from the last glaciation. We have some moraines. And then we have to go a couple 200 million years to see the next bit of Earth's history.
My
That's a
goodness.
lot of
Yes.
missing time, and that time is all in the ocean. So we can go to the ocean and see it. So it's a fairly continuous record. It's not absolutely continuous, but it's as continuous as we're going to get. And one of the amazing things about ocean drilling is you have this or fairly continuous record. We need really continuous records. And so instead of drilling just one hole at a site, they drill 3, even 4 holes. So they're able to put together what's called a composite core. And so they know, because if you think of drilling, when you go down with the core, you tend to mess up the bottom a little bit and mess up the top or the next one a little bit.
Mhm.
And so you have a core now this way and then a core this way. So
Mhm.
they hopscotch around each other so that you get a beautiful record. And what you can do with that is look at what is causing the changes, because we don't know. We know for the last 5 or 6 million years that climate was driven by orbital forcing, the relationship of our planet to the sun. But we've had that relationship to the sun
Forever.
for a billion
Milankovitch
years,
cycles have existed forever.
and
Yeah.
we don't see the so it's
Yeah.
sort of like you did this and then this happened, but you can do this
A million
and
times
this
and then you don't
doesn't
see it.
happen, and this
Yeah.
doesn't happen. So what triggered that? And I'm going out this summer, and that's one of the things we're gonna be looking at is, particularly for the Northern Hemisphere, when did the glaciation start? When did the bottom currents change? What
Very
happened?
cool.
Because we hope to get into the older parts of the sediment, so beyond 5 million years,
Very cool.
to see what ocean currents were like, the bottom currents, not the
Yeah.
surface currents. And, it's the only place we can do it. You can say, well, you could look in lakes, and you can look in lakes, but the chances of finding the 5 million year or 10
No.
million year old lake sediment, not so much. There's Lake Baikal in Siberia where they did some of that, and it's fascinating work. But that's one spot. And in the ocean, you can go lots of spots and try to figure this out. And we still haven't figured it out, but we know better what questions to ask. We know better where to go to answer those
Mhm.
questions. And I think one thing people also don't realize, when you drill a hole, that is tied into a seismic line.
Yes.
And there's all this, what's called site survey work that's done, and people go back and forth with a ship that's able to listen to with energy, the changes in density of the ocean sediment. So you have an idea: is it nice and layered? Is it all messed up? Is it big fat layer?
You get a better idea of structure
Ah,
and units usually of like resistivity, right? A better overall picture of the environment.
right. And so it's one hole, but you can extrapolate then over much
Mhm.
longer areas. So even though it's sad, it's just one hole, you can extrapolate a lot, figure out more about what the ocean was like at that time. And that becomes really critical because people look at these, they're called reflectors, some major reflector where there's a big density change. And you might say, okay, this reflector means something.
I think that's a fantastic answer, Suzanne, because I think that's perfect on preservation, and I think you're so right, like, the ocean drilling is one of the only times that we can get a complete record of marine sediment and marine history, and we can get a deep record and an older record that's not available on land. I love scientific ocean drilling, I just have always been absolutely obsessed with it ever since I was a kid, and I found out what Jacques Cousteau was. I was like, "I'm gonna get on a research vessel, and I'm gonna get on a drilling ship. It's gonna be my job." One thing that you brought up there is understanding kind of climate change and understanding Greenland and up in the North Atlantic. When we talk about climate change, I think so many people are obviously so interested in it, but they might not understand it, or they'd be really interested to hear your opinion of it being a senior climate scientist. I was wondering if you could speak to climate change in the future. What's something that worries you? What's something that gives you hope? And then what's something that you think people should be more aware of in terms of climate change?
Well, needless to say, I talk to people about climate change all the time.
I love it. Good.
That's what they say. It's really important to talk to
Yeah.
people. So if you were to sit by me on an airplane or a train, you would think, oh, I have to change my seat. But, so first, there's a lot we don't understand. And so sometimes people say we don't understand, but there's a lot we do understand. And I think as a scientist, we often focus on what we don't understand because we want
That's our
all the
job.
answers. Yeah, it's our job. But we know for sure we're putting a lot of CO2 into the atmosphere, and we know for sure that is warming it up. We might not know exactly what the consequences are. Like we might not know how fast Greenland is melting. It was just a paper this week about that it looks as if parts of a northern glacier in Greenland is melting twice as fast as they thought.
Wow.
So there's so much we don't know, but there's so much we do know. And I think people don't understand the situation of the rate of change. So often people will say, well, climate has always changed. Yeah, but it didn't change
Slow.
this fast.
Yes.
When
Yeah.
it changed this fast, we have things like the Cretaceous Tertiary boundary.
Yeah.
We have other major boundaries, and even those boundaries are not as fast as our current rate of
And they're
change.
also associated with mass extinction events too. Like that type
That's
of change is chaotic to the entire system.
and it probably didn't happen as fast as what we're doing right now. If you consider that in what, about 200 years, we have increased the atmospheric CO2 by about 50%. So I don't remember the number, but it's something like we have detonated the equivalent of 35 billion, and then it is a billion Hiroshima atomic bombs. We've
Oh
added
my
that amount of
goodness.
energy. The thing is, this energy that's coming in, 90% of it goes into the ocean.
Yeah.
So the ocean is warming so fast. It's a huge water has a very high heat capacity. So it takes a lot of energy to warm the ocean. And we are warming the ocean so fast. Some papers show that the surface 10 or 20 meters, but now it's showing that that warming is going down well over 1,000 meters.
Oh my goodness.
Yeah. So we're changing this major source of our food, of climate, of ecosystems, and we're doing it so fast. And so I wish people understood the importance of the rate of change. If it happened over 2 million years, that's still fast for geologists, but it's
Mhm.
not like you're doing it over 300 years and that's what we're doing. You can't even see that in the ocean record.
No, not at all. It
So you
won't be
wouldn't even
preserved.
notice. It would just be a thin line, just like the thin lines that we see where the KT boundary is or something that was, and that's what we're doing. I wish people understood that more. I think they would get on faster doing things. And in terms of hope, I think hope is really important. People say, oh, how can you teach these courses? It's because I do have hope. There
Yeah.
are so many new things that we can do, the new sources of energy. I don't understand why we are not putting huge amounts of more money into research for alternative energy, why we aren't providing funding like low hanging fruit, yes, but why aren't we subsidizing all these houses being insulated so they aren't
Yeah.
using as much energy? We
Easy
would all
solutions
benefit.
to it.
Yeah,
Yeah.
it's so easy. And when I say our planet, I mean us. That's what we care about. I care
Yeah.
about the planet itself. Earth isn't going to be fine. The dinosaurs went away and it was fine.
Yeah.
Trilobites went away and it was,
Yeah.
but it's the humans and the real devastation that could happen as we have more climate migrants, as coastal people lose
Their home.
their place to live.
It becomes a nuanced, complicated human problem of like policy and economics too.
Feel as an educator that maybe we are not doing our job, that we need to have everybody understand, not just say the words like, oh, climate change is bad, but why is it bad? Examples of the consequences and the increase in fire, the increase in storms, the rise in sea level. There's so much that people need to know about. And I think they don't understand why they don't act. And students today, I'm very fortunate to work with really great students. It's a very liberal place. But even then, these students are driving around in these big cars and they drive from one part of campus to the other and
It's not
drive.
front and center, like at all times of the importance of climate in everyone's everyday lives.
I think understanding all of these different parts and then just becoming a leader in it, like in your own way of saying, all right, I'm not going to take 20-minute showers. I'm going to eat beef less, only once a week or once a month or
Yeah.
whatever it is. Just making small changes and talking to people about it. Like, why am I doing this? Because I care about you. I care about humans. I care about the next generation.
Yeah. I think that's a really good answer. But I do think that you need a little bit more education into what is the consequence of climate change. And also, I think the interconnection of resources. I didn't understand how many resources and energy was tied into our everyday kind of consumption until I worked in mining, just realizing how reliant we were on natural resources. I didn't realize how much we use, how much goes into every single movement from showering and electricity and energy to technology and the amount of rare earth elements that are within all of our technology. And that has to be mined. And that uses diesel, that uses oil and gas, that like the
And
interconnectivity
it
of
pollutes
everything.
water.
Yes, the whole thing.
And of course, now with the need for rare earth elements, and one of the places they can go to get them is the ocean.
Yes. Yeah, that's true.
So ocean mining is not something in the distant future. It's something in the near future,
Yeah.
which I think is terrible because one of the places they'll go is, are these amazing, fantastic vent communities,
Yeah.
which are like fairy tales in the deep ocean.
Yeah. Agreed. It's hard to mine in the ocean without consequence. It's hard to mine on land without
Mhm.
consequence, without environmental consequence. Suzanne, this is switching topics completely. And it's going away from science and from climate change, but going into a different passion of yours, which is DEI. And I just wanted to talk about and touch on your book that you wrote in 2015, Women in the Geoscience: Practical Positives Practices Towards Parity. Could you describe the book, the inspiration behind writing it? And I know that there was a bunch of practices that came out of that book of what we can do to increase parity in geosciences. Could you maybe speak on those practices?
So that book actually grew out of a program at the National Science Foundation called Advance. It changed so many things. Prior to Advance, I've been around in this business a long time. And when I started at Wesleyan, I was the first and only woman in geoscience, physics, chemistry, astronomy.
Whoa.
And it was a very alien place. And it
I
wasn't
couldn't
that long
imagine.
ago. It
No.
wasn't that long ago. And I still remember going to a meeting. It was actually a scientific ocean drilling meeting early in my time at Wesleyan, and there were 80 men in the room and one woman,
That was you.
me. And so that would never happen today. That would never happen today. And one of the things was that the National Science Foundation realized that the numbers of women were aligned like this. And instead of going like this, and oh, eventually it's going to happen, we're going to get there. We're never going to get there.
Still
The
this.
line is like this.
Yeah.
We're never going to get to here. They put a lot of money, millions and tens of millions of dollars into this program Advance. And instead of it being like, okay, you get money for something, for whatever it is you want to do, the institution would have to buy in. So like the provost, like a very high
Yes.
person,
Yeah.
it isn't just like me in my little lab saying, oh, we need to increase the number of women. No, it's the provost saying,
Amazing. Yeah. The head honcho.
and they put money into it. So it was like, oh my gosh, I have an NSF grant for $500,000. Wow. Somebody is paying attention. So they put the money in, and a couple of the schools, the one that stands out most to me was Michigan. Their advanced program was the first set of advanced schools. And they looked at things like, what are the barriers to hiring, say, more women? Because women were getting degrees, but they were not joining assistant professors. And then they
They
certainly
weren't
weren't
moving.
becoming
Yeah.
full professors. Even if you got your PhD, you were leaving. And why were you leaving? You know, women want to have children. And there was no family leave policy. There was no nursing facilities. There was no daycare. There was all these things that schools needed. And then also a particular problem, I think in science, but probably everything, in a profession, you tend to be married to someone with a similar profession.
Yes,
Like
it's true.
doctors marry
Yeah.
doctors or nurses, and lawyers marry lawyers. And so you as a PhD geologist is probably married to another academic, quite likely a geologist. And so one of the things they did, instead of looking at it as a two-body problem, a two-body opportunity. And so what would happen is so they want to hire this female person, or they want to hire the male. And the female, what's she going to do? She has a PhD too. And so they had money in this so that you, as a trailing spouse, could come and get a job for at least 3 years, could
Amazing.
establish a lab.
Yeah.
And it was part of the grant. And this is something we write about in the book, the whole idea of implicit bias. So
Okay.
people have known about this for a while, but I don't think they internalized it. One of the examples they use a lot is orchestras used to have only men. I remember as a kid I lived near the Boston Symphony Orchestra's summer home. They were all men. When they were trying to change this, they made it so that everybody was performing behind a curtain, and they
Oh,
was blind. And then all of a sudden, guess what? They were really good female musicians.
oh, wow.
But then if you saw a woman playing a violin, you couldn't imagine she was really good. But if you didn't see her and you didn't see anybody, she was really good. So the whole problem of dealing with implicit bias, and one of the things they did at Michigan is they had I don't think they were called Michigan players, and they would act out these scenes, and it would start out where there were, say, 4 people, and it was a white professor, a black professor, another couple of other people, and they had all these different roles, and they'd say these things. And then they would switch. So now the woman would be the aggressor person, and the male
Yes.
would. One of the things we did with our advanced grant is we brought those players to the American Geophysical Union meeting, and it was open, and people could just come for free and listen and see. And you would get really angry, like, why are they doing that?
Yeah.
And then they would switch. It was like, oh my gosh, I have a totally different emotional
Viewpoint of that,
reaction.
if that behavior is allowed when it's associated to a different person or what that means. Yeah.
Yeah. So advance really got implicit bias in the sciences rolling. Also, like questions that you could ask at an interview. So you could no longer say, are you expecting to have children?
I've even gotten those questions, and you're
Yeah,
like, "That is so illegal. You're not allowed to ask that."
we just had a couple of searches in my department this year. And when we have our initial meeting with these people, we have the same 10 questions, and everybody gets asked the same 10 questions in the same order. So it isn't as if I can start saying, oh, you're doing something I'm really interested in, so I'm going to delve into that, and you're going to become my favorite person, and you're going to get my vote.
Yes,
You
because
had
we've
to ask
established a
them.
bias. Yeah.
And so they did work like that, showing how important that was. And these are things that are in our book about that. And then just the whole idea of mentoring. And I think there's a organization, National Center for Faculty Development and Diversity. I first became acquainted with them through an advanced workshop that I went to. It talks about what is important in terms of moving your career forward. So when you look at it, the females tend to be put on more committees because you need to have a female or a minority person on these committees. And that is getting you nowhere.
It's tokenizing you.
And so ways to say no, and also to point out that, hey, if you only have one woman, she cannot be on all the committees.
Yeah.
It's just not fair to her. And So just things that now might seem like common sense. Even then, they might have seemed like common sense, but now it's incorporated.
It wasn't being incorporated or practiced then, even if it was common sense, it wasn't actually realistic to that
Right.
environment.
I think the advanced program, and this book is a distillation of a lot of the advanced programs. And it's just a great program. I think
Amazing.
it changed so many schools, and if all the other schools are changing, then you have to
Yeah.
change too. New ideas or ways to deal with things. The trailing spouse, making a position for that person and looking at it not as a burden, but as an opportunity.
To get 2 birds with 1 stone. That's an
Yeah.
amazing mindset to look at for faculty, but also just a very easy implementable change that can add
Mhm.
women into the faculty and to academia. That's amazing.
Or the woman couldn't come because her husband didn't have a job. Now she
Yeah.
gets a job, but he gets a job too.
I definitely went to both of the schools that I went to for undergrad and grad school. We had so many spouses that were both professors, or one would run a lab and one would be a professor, vice versa. And it was fantastic. They came together as a pair.
Yeah,
Yeah,
years ago, and I think people as young as you don't remember this, but I remember this. There was these rules called nepotism rules, and you could not hire the spouse of someone. You were forbidden to hire the spouse. Then what are you gonna do? I just have so many instances in my head where it would have made so much sense to hire them as a team, but
totally. I'm happy that program advance was put into play and that you published your book and all of these findings from the book is absolutely incredible. One last question is, Suzanne, you've just been like, you're a legend in this field. You have been working in oceanography, ocean drilling, climate change for years. Could you maybe describe how this industry has changed since you first started your career? Where would you hope the future of this industry goes? And then what would be any advice to people just starting this industry? So, how has it changed? Where do you hope it goes? And any advice to someone just starting right now?
let's take one, like what has changed. I'll just give one example of what's changed, and specifically with ocean drilling. If we look at the Glomar Challenger that was around for 12 years, the f on the second expedition, they had 2 women,
Wow.
micropaleontologists, out. But that entire time, there were 3 women co-chiefs.
Oh my goodness.
3 women out of 96 legs.
That's crazy.
That's crazy. Whereas now, it common, not common, but it happens so that nobody blinks. You have 2
Too.
women co-chiefs.
Yes, you do. Yes. I've sailed on multiple expeditions with both
Yeah.
women co chiefs.
Almost every expedition has at least one woman as
Mhm.
a co-chief. I mean, that's such a tremendous change, and on leg 74, my first leg, there were no women on the cleaning staff, there were no women technicians, but now it's I think more than half the technicians are women,
Yeah.
and people that do the cleaning and cooking are at least half women. I think it just changes the whole atmosphere. If there are 2 women and 100 men, it's a very different situation than if there are
50-50.
50 women and
Yeah.
120 men. It's very different. So that's one thing. That's changed so much, and it changes so much, just the way things feel. The future. So I think we're in a really sad place for the future because, as you've probably heard,
Yeah.
the Geordie's resolution is going to be tied up,
Yeah.
which is unbelievable to me because we have so much more to learn. And it's as programs go, if you look at NASA, we're just a small mission in NASA. The
Mhm.
fact that it's tied up, my hope is that people will realize, and this is National Science Foundation, that it just has to go on. That so we as scientists need to be lobbying congressional people much more strongly, and not only in the U.S. but in the world. Because part of the reason the National Science Foundation pulled out or is pulling out is because that the international partners aren't able to pay as much.
Yeah.
Because I guess I have no idea why. You might think Japan, they have a huge space agency. They could put in some money. All these countries still have
Yeah.
space agencies, and this is our own planet. And so in terms of what I'd say is, in terms of your own, what you're doing, be present where you are. So be where you are. Enjoy that moment or not enjoy it, but be present
Be
so you
in it.
fully experience it. And then I think be resourceful because there are resources out there. You just have to figure it out. And then I do have a lot of hope for the future. If you don't have hope, then you may as well not bother to do anything. Or I guess, I don't know. I have hope in this new generation of students, in the technology, that people are going to wake up and you might say, we're going to exceed 2 degrees C. Yeah, but let's make sure we don't exceed 5 degrees
Yes,
C.
let's try to cap it or try to manage it a little bit better with technology or policy or whatever, what
Yeah.
have you. I think that's a great way to end it. And I love the hopeful nature. I couldn't agree more. I think if you're not hopeful, I feel like you become apathetic and you don't want to change anything. I love the idea of being present, especially after hearing your story of how you became involved in climate science and this kind of serendipity aspect of it of just being like, I don't have a car. Can I come with you guys? And then that led down a full path of working for Woods Hole and oceanography. So I think that's fantastic advice. I couldn't agree more with your answer, Suzanne. And just thank you so much for coming on to the show. I learned so much. I hope other people learned as well and enjoyed listening. And just thank you for coming on the show. It was so nice to see you again.
See you. And I think thank you for doing this because I think that people just need more exposure to some different types of information so that they don't lose hope or they don't think it's only getting worse. It's not only getting worse. Many parts are getting so much better.
And it's not concrete yet either. I think that becomes a thing of like, it's getting worse. Like we can still do better. We can still change it. We might not hit the two degree, but we can, like you said, cap it before it gets to 5. Amazing. Thank you so much.
Thank you and take care.
Thank you. Bye, guys. This has been the Smoko podcast. We will see you next week. Thank you so much for listening.